I'm Ursel Bangert, a physicist and Bernal Chair in Imaging and Microscopy at the University of Limerick in the Bernal Institute. I would like to introduce the impressive electron microscopy facilities which we have in the University of Limerick. With transmission electron microscopes, TEMs for short, one can image materials down to the atomic level and reveal the arrangements of atoms. Here you can see, for example, what it looks like when we focus into a pencil tip. So from the graphite pencil tip we take a bit and we look at it in the microscope, then we look a bit at a smaller region, enlarge it. So we take a little flake of that small region and put it on a so-called TEM grid, because that's what we need to put into the microscope to be able to look through. So there you see the flake. It's transparent, and enlarging it a bit more, and that is the end of the enlargement you can get with a light microscope. So now we've put it into the electron microscope, and you can just see in the top there is a bit of a bit like a transparent eyelid. There is this flake that was just shown before, and we're now on the micron scale, and we go in, and disappointingly what we see is just crud, so that's the contamination of the material, which is usual. But if we then zoom into a clean region, we can actually start seeing a background pattern, and there we see it, atoms. This is the lattice of graphite or graphene, and we can see the atoms are actually spaced with 1.5 angstrom, at 1.5 angstrom. So the newly installed FEI Titan Themis TEM in the Bernal Institute at UL does not only enable researchers to see individual atoms, as I've just shown an example of, and identify their chemical nature, and on the scale of several tenths of billionths of a millimeter, it makes it furthermore possible to observe materials dynamics on the sub-millisecond time scale. And this is due to an addition of a super fast and sensitive camera. Furthermore, it's possible to observe materials reactions under heating and biasing, in liquids and also in gases. And this is due to the new in situ holders we have acquired. And all this can be done on the atomic scale with atomic scale precision. On the left-hand side, you see the Titan Themis cube. So the actual TM is encased in a 4-meter high cube to protect it from environmental influences like temperature fluctuations, vibrations, and magnetic fields. Because we want to see things on the atomic scale, we need to have everything dead stable.
My name is Jennifer Cookman. I'm a postdoctoral researcher in the Bernal Institute, and I work with Professor Ursel Bangert. So I'm working on a project funded by the EU called MagnaPharm, and it works on investigating how the magnetic field can affect crystal structure growth from pharmaceutical crystals. By using an applied magnetic field on the growth of pharmaceutical crystals, we can gain access to different crystal structures that could potentially have improved properties and make more improved pharmaceutical treatments. The 4-meter tall transmission electron microscope that Ursel mentioned has an atmosphere that's very space-like. So it has a high vacuum, and generally things that contain liquids cannot exist. To look at the pharmaceutical crystals grow, I use a special holder that's basically like a transparent box. This encapsulates liquids and also gases so that the electrons can transmit through the box easily, and we can look at processes happen in front of our eyes. When I put a liquid inside this box that contains molecules of the pharmaceuticals, we can see things happening, as you can see in the video playing at the moment, where crystals just form out of the blue as if there's nothing there in the first place. So these kind of processes we can see in real time, and it's absolutely incredible. Using this kind of transmission electron microscope, we can see these processes even down to the atomic scale. So if we can scrutinise and really investigate how these crystals form from the atoms up to their pharmaceutical crystals, we can really then understand how we can get better properties to make more efficient and more effective pharmaceutical treatments. Having access to this kind of equipment gives us access to avenues of creating collaborations with many companies and universities, and at the moment we have very exciting collaborations to have a look at in situ processes of organic and inorganic materials. This kind of visually revealing research down to the atomic scale is one of the many exciting reasons that I chose to study chemistry for my undergraduate and also my PhD. And it gives me an opportunity to make a broader impact on health and the environment and also technology.
Okay, so if you want to find out more about what we're doing or even want to engage with us, please contact myself.